Okay. Let me welcome you to this fourth lecture on our course on reinforcement learning. This one is the last lecture from a series of introductory lectures that aims to set the foundation of what we will be doing. After this lecture, we're going to get in more detail on specific topics like rollout, policy duration, training of neural networks, and other things. What we're going to do in this lecture is revisit POMDP, partial observation Markovian decision problems, then talk about systems with changing parameters and the general area of adaptive control in particular, then talk about model predictive control, and also we're going to overview the overview lectures. So here's the outline. We'll start with problem formulations and continue from where we were in the previous lecture, go into partial state observation problems, then go into adaptive control, and then we'll take a break, go into model predictive control, and then we'll have an overview and map out the future for the course. So problem formulations and reformulations. How do we formulate practical dynamic programming problems into the mathematical format that we have been using? And I mentioned to you an informal recipe, the one that I use. First, define the controls. These are fairly obvious from the practical situation. Then look to define the stages at which control is applied. And much of that is determined by the information available at each stage. Basically, if you have information coming in that's useful at every stage, then you align the stages with the flow of information. And then you have to define the states. Now, the state is the trickiest part. And the guideline here is to define a state at time k, xk, something that summarizes the past. Everything that you have seen up to that time that's relevant for the purposes of future optimization. In other words, as long as you know xk, all the other information from the past is irrelevant. xk summarizes the essential content of the information that's useful for future optimization. And the idea is that the controller applies action that depends on the state. So the state must subsume all the useful information, useful for decision and control. Now, that's easier said than done, but it's a useful guideline. There are multiple useful ways to define a valid state, and we mentioned POMDP, partial information Markovian decision problems, where at time k, we do not observe the state itself, but rather obtain a measurement, which we call zk, that is related to xk, probabilistically related. For example, xk might be a 6-dimensional vector, and zk may consist of only one component of that vector, or 3 components plus some noise, okay? That's the kind of measurement that's an example of a measurement. It tells you something about the state, but it doesn't tell you the state itself. So what is the useful information that you have at time k? Well, what you have seen are the measurements or observations, Z0, Z1, up to Zk. And also you remember the controls that you have applied from the past. That's where you are as far as you know. And that indeed can serve as a state that evolves over time. From Ik, you get a new measurement, you get a new control, you go to Ik plus 1. That's a dynamic system conceptually. Remember that in our course, the state is not a nifty finite dimensional vector. It can be anything, right? Including sequences that are expanding over time. So it can serve as state, is the most straightforward possibility, but there are also other options for POMDP. And before I go into that, well, I mentioned one other option last time, the probabilistic state, namely the probability distribution of the state given all the information that you have obtained so far, what we call belief state. But let me first give you an example of an imperfect state information problem. This is sort of an academic example, a parking problem involving a car that wants to park along a line of parking spots. There are M parking spots, and it's looking to find a free spot. And if it finds a free spot at some point, let's say M, then it has the option of parking at this cost. Or it can continue trying to find a cheaper, a better parking spot. So at every time step, we move one spot in either direction, and we decide to park or not to park at a spot M if it is free, and then we pay a cost C of M. And if we have not parked by time N, then there's a large cost. So basically, we want to park within N time periods, N stages. N can be a large number, and or it may be not much larger than capital M. Now, what are the observations here? Well, the car moves from spot to spot and looks at the spot and can determine whether it's free or it's not free. But it cannot tell whether the next spot or is free. It can only observe one spot at a time. Moreover, the parking spots may change status at the next step with some probability. Someone may come into a free parking spot and take it over, or somebody who is parked already at a spot may leave. So the state of the parking spots is unknown at any one time to the driver. He only has the information about the spots that he has seen, but he doesn't really know whether the information is up to date. So, however, the driver can estimate the status of the parking spot in a probabilistic sense, in that it can calculate the probability that a spot is free or taken at any one time. So the free taking status of the spots is estimated in a probabilistic sense based on the observations. So the observations were current at the time they were taken, but they may not be valid anymore. The status may not be valid anymore in the future. So what should the state be? According to our guideline, it should summarize all the information needed for purposes of future optimization. So the first candidate for state is the entire information vector, all the information that we have seen so far. Another candidate, however, which makes sense, is a belief state, namely the conditional probabilities of the free taken status of all the spots. So P of 1 is the probability that spot 1 is taken. P2 is the probability that spot 2 is taken. One probability for each spot conditioned on all the observations so far. And these probabilities change over time, right? As time progresses, slots may tend to fill out or may tend may tend to be free. So there is a certain dynamic equation that governs the evolution of these probabilities. These probabilities depend on time and also depend on the observations that we take, right? So we can view this as a dynamic system, the system whose state is the belief state, and it evolves through time through a dynamic system of the type, conceptually, that we have seen before. So here is a generalization of the idea that I discussed in the context of the parking example. You have a belief state, which I call BK. BK is a probability distribution of the state XK, which is unknown, probability distribution conditional on all the observations that we have seen so far. And that belief state evolves according to some system equation, which we call the belief estimator. It's really an estimator of the belief, and it evolves over time. The belief at time k plus 1 depends on the belief at time k, and the UK, the control that you choose, and the observation that you get. So all the probability distributions for this equation, probability distribution CK plus 1 and so on is given. So by Bayes' rule, some form of Bayes' rule, some kind of an inference equation, you can write down this system here, the estimator. Now, I'm not saying that this is easy to write down, but in principle, it exists there. And we can also consider the cost of a transition to be the expected value, the believed cost, the expected value of the cost based on the belief state that we are right now. So we are at belief state BK, a new observation comes in, control has been applied, we apply this equation, we get BK plus 1, and so on. This belief state is fed into a controller, which is a feedback controller, applies an action depending on the belief state that the estimator has provided. It applies it to the system. This estimator continues for one more step and keeps going. So, okay, it may be a little difficult to wrap your head around the details of this, but conceptually, it's not different than the stochastic system control that we have seen so far. And it has a dynamic programming equation in principle. In principle, you can apply dynamic programming with cost to go function JK star that depends on the belief state, right? Because we're considering this problem involving beliefs, not the original. And it's given by the usual type of formula. We consider controls UK within some constraint set, and we minimize the sum of two costs. The current stage cost that depends on the belief state and the control, and the expected optimal cost to go, which is J star of K plus 1 at the new belief state, which new belief state is given by this equation. And the expected value is with respect to Z, because we don't know the measurements that we're going to receive. They depend on BK and UK, and this probability distribution can be estimated. So in principle, this expected value can also be estimated. So the first term depends on BK and UK. The second term depends on the conditioning variables, which are also BK and UK. So the entire expression within brackets depends on BK and UK. And when you minimize over UK, you get a number that depends on BK. And that's the definition of the optimal cost to go. This is just the usual dynamic programming algorithm, but it has been lifted into a belief state setting. Okay, let me finish this slide and then you can ask questions. Okay, but like I said, UK is the control constraint at time K. G hat K, this is the expected cost of stage K. It's the expected stage cost. If this is given, is the expression given for the original problem that was given in terms of XK. Expected value of that with distribution of XK and UK determined by UK and the distribution of WK. All of this takes some complicated probability calculations, but conceptually they're very simple. And even though the calculations are a little tedious, in the end, conceptually, it's just what it is. Expected cost given the belief state, believed expected cost for the stage. And as I mentioned, this is the belief estimator that gives the next belief state, given the current belief state, U and the observation. So in principle, partial state information problems are not different than perfect state information problems, conceptually again. And in fact, there are two different ways to reformulate them as perfect state information problems. One where the state is the information vector, that's a useful formulation in some problems, or in this form here, in terms of the belief state. That's very common, and in artificial intelligence, it's actually the preferred the preferred mode of formulation. Now you have formulated this, but that doesn't mean that's easy to solve. It's extremely difficult to solve. Solving exactly this algorithm can only be done in problems that are so simple that that you wouldn't even look at them. Okay. For any other problems involving, like, say, three states or something like that, it's impossible computationally to carry out this algorithm unless you have very special structure, of course. Like the parking problem, for example, has some special structure that allows, okay, the parking problem, a simple versions of the parking problem, you could apply exact dynamic programming to them. As long as you have 3 or 4 spots, then it becomes difficult. On the other hand, difficult as this dynamic programming algorithm is, it can serve as a starting point for approximations, for reinforcement learning. That's the starting point for reinforcement learning to come into play by using, for example, approximation in value space, where you replace J star K plus 1 with J tilde K plus 1. How do you get this J tilde? It could be rollout, it could be training, it could be many different things. Once you have a J tilde trained, then with online play, it's not difficult to crank this equation forward and calculate controls. So that's the game plan as far as partial state information problems are concerned in the context of approximations and reinforcement learning. Start from a conceptual, exact point of view, and then introduce approximations to simplify the calculations. Any questions?
Estimator given by nature, or it is something that okay, it's
okay, a common type of estimator in some type of problems involving Euclides is the Kalman filter. Have you heard of the Kalman filter? It's a very common estimator. Well, it's an example of a belief estimator, and it calculates Gaussian belief states. And it calculates the mean of the Gaussian and the covariance of the Gaussian, and that's enough. Now, that's one example. There are also other examples that are sort of, the Kalman filter is the best representative example that for which you can write down explicit formulas. Others exist, are more complicated. There's something also called the particle filter. I don't know, some of you may have heard of particle filters, which generate by simulation these belief probability distributions. So you have, with a particle filter, some kind of distribution, and then you run a simulator and simulate where the next states may be, accumulate the probabilities, normalize them, and so on and so forth.
What are the properties of the belief estimator? Like, are there any guarantees that we can make to have a good belief estimator?
The guarantees for a belief estimator are outside the guarantees, are separate from the guarantees of the control context. Like how much error you make in terms of the optimum. But yeah, what I mean to say here is that there are two separate issues. Now, the better estimator that you have, if the belief estimator is better, then certainly it's natural to expect that your control scheme is going to perform better. The suboptimal control scheme that you get would control better. Now, if your question has to do with can guarantees on the belief estimator be translated to guarantees on the quality of the control, then that's a very difficult question to answer. I don't know of any, in fact. I don't know even of any instance where you can give explicit guarantees. It's like in reinforcement learning, anything goes. And we can't really tell when we have succeeded. Okay, I don't mean to disappoint you, but that's the way it is.
Sure. I'm just curious, like, if I have a really good belief estimator, for example, just gives me like DK equal to XK, or like equals to partially observed state. I mean, wouldn't that allow me to make a problem of MVP, for example?
It all depends on the problem. This these POMDPs are so idiosyncratic that you can't really make too many general statements. In fact, the only general statements that you can make about them are in this one slide, okay? The rest is problem dependent, and you can go from success to failure very quickly here. These formulations and computations are so sensitive to various choices that you make, which are very much tied to the structure of the problem that you're dealing with.
Professor, I have a question. I'm online.
Yes, speak up, please.
So the UK is the control constraint set. Can I understand it as just the action space? So you choose from one control from this set, right?
Yes.
Okay. So I'm just confused a little bit about the constraint part. So it's basically an action set. That's it. Thanks.
Yeah, it's an action set like the ones that we had before. There's an important detail here that I haven't mentioned, namely that this UK does not depend on the state. If you remember, in a standard formulation, UK depends on the state, right? Here it does not depend on the state, primarily because the state has changed. It's BK, which is a more difficult object to deal with. Any other questions? Okay, we will have an opportunity to look at special cases of partial state observation problems in the future. But for the time being, we're going to leave the topic and go into adaptive control. Adaptive control refers to problems where the system equation involves parameters that may be changing and may not be measurable. They can be estimated, perhaps, but they are not measurable. And also, you have to plan accordingly. You have to plan according to the fact that there will be changes in the system parameters, so you may want to be conservative, just in case the system parameters change on you in an unfavorable way. This type of situation, change in system parameters, occur very, very often. The subject of adaptive control is very old, goes back to the 60s, was a hot topic when I was a PhD student. And people are still working on it, primarily because it's a very, very difficult problem in general. However, as I look at these self-driving cars that go around Tempe, and I'm scared that they might run me over, I take heart and I celebrate the successes of adaptive control, because self-driving cars involve adaptive control for sure. So let me give an example here. A simplified problem of adaptive cruise control. Okay, here the objective is to keep the velocity of your car close to some target level that the driver may set. Says, I want to drive close to 60 miles an hour. I want to go 50 miles an hour, something like that. So we want to regulate the velocity of the car. And the car's velocity at time k is denoted by xk. And according to this simplified model, it changes according to this linear equation, where A is a coefficient that models friction, wind drag, and so on. So the velocity naturally tends to decrease. In the absence, if you didn't press the gas pedal, the velocity of the car would decrease. And there's another term, which is an acceleration term. UK relates to how much you push the pedal, how much propelling force you apply to the car. And there's also a coefficient B here, but that B is not really known, and it changes all the time. Depends on the road, whether it's bumpy or uphill or downhill. It depends on the number of passengers are in the car. So you can't really know this B ahead of time. You have a situation where the velocity of the car evolves according to unknown parameters or parameters that are maybe hard to estimate. So this is our system, and we want to control the velocity. And let's consider a quadratic cost function. We want to keep the velocity over time, over n periods, close to some target, x bar, okay? So we penalize the distance from x bar, and we also want to do it with not too much acceleration, okay? So we put a quadratic penalty of control, and r, the coefficient, is given. So if we knew a, b, and x bar, then the problem would be simple to solve. It would be just a variation of the Riccati equation type solution that we have gone through. On the other hand, a, b, and x bar are changing all the time, and they may be measured, but with error, okay, if they can be measured at all. Why is x bar changing? Well, the driver may set the velocity at some value, like 60 miles, 55 miles, 50 miles, but also your system has to have the capability of slowing down automatically, at least in some versions of this problem, when there's a car ahead, okay? If there's all of a sudden there's a car in front of you, you have to make the velocity lower, set a target velocity somehow, and try to reach this velocity gracefully through this linear quadratic formulation. I'm not sure I would want to use that cruise control like that in my car, but that's a starting point for more complicated, more sophisticated cruise control systems. And some of these are actually implemented in cars that you can buy today. They have been for a few years implemented. So this is an example, a simple example of adaptive system and adaptive control, unknown parameters. There are many other examples. Problems with robotics are typically adaptive control problems. In robotics, you want to have a robotic arm, take a weight, let's say, and put it over here. However, the weight is an unknown parameter often, okay? And that will affect the dynamics of the transfer. And there are many, many examples like that, including chemical process control, including all sorts of control systems, and in reality involve adaptive situations. So adaptive control deals with a situation involving changing parameters. And how do we do that? Well, I'm going to discuss here 3 different approaches that you can take towards this problem. The first one is to just ignore the changes of the parameter. Design a controller that is robust, quote unquote. In other words, it works for a broad range of parameters. So you expect your parameters to be between 5 and 10. You design a controller that works well throughout the entire range, if you can do that. That's called a robust control. It does not make an attempt to adapt itself. It's just pre-designed and hope for the best. The second possibility is to actively try to estimate the parameters and use the estimates to modify the controller. And one possibility here is to do online replanning by optimization. In other words, you have a set of estimates of the parameters, and you modify the controller to make it optimal for that estimate, not for future estimates, not for future values, for what you believe is the current set of estimates. It's a very popular approach to adaptive control. It's called indirect adaptive control, and I'm going to discuss it in one of the following slides. Now, reoptimization has to be done online, right? You estimate parameters online, and then you reoptimize online. But this reoptimization may be time-consuming, and you may not have a big enough computer, or you may not have enough time to do the reoptimization. So it could be done suboptimally, and that's where reinforcement learning comes into play. Again, we can do online replanning by some suboptimal method, like rollout. It's a very good alternative to reoptimization and faster. Rollout with a base policy, which cost values are computed using the current parameter estimates. So this is rollout using the estimated values that you get from the estimator. So this is a simpler and faster reoptimization. So we have robust control. We have this indirect estimate optimized type of control. And there's a third possibility, to view the entire adaptive control problem as a POMDP, where the parameters are estimated and they take part in a belief state. Now, this is more principled, harder to apply, but there are contexts where it makes sense, including a context that I'm going to discuss today and later in the context of Bayesian optimization. So these are the three possibilities, and I take them one by one. Questions? Okay, so robust control. We ignore the changes in the system. So this is a changing system. It produces an output, a function of the state, and we have a fixed controller that doesn't take into account the changes. And it applies control, and this thing keeps going. So we make no attempt to estimate or to learn the parameters and hope that the fixed controller will yield acceptable performance throughout a range of system changes. You may say that this is simplistic, risky, and so on, but it is simple indeed. And if it works, it may be fine. For sophisticated modern applications, high-dimensional applications, it's becoming more and more difficult to apply this approach. But over time, there has been a timed-honored successful example called PID control. How many of you have heard of PID control? Okay. It's used very widely in industry for chemical process control, for other types of control. And PID stands for proportional integral derivative. And this controller involves just three parameters, which are tuned experimentally or heuristically on the given system, but without constructing a model of the system at all, okay? It's not an xk plus 1 equals f of xk and so on. It's just something that from which you get input-output data, and you tune these parameters on the system itself. And there are three parameters, okay? So the controller is measures the level of the output and its distance from set point. Let's say you want to set the system to operate at value 10, and then it produces an output that is 11, okay? The difference is multiplied with this proportionality constant and is fed into the fixed controller. There's another parameter that accumulates, that multiplies the accumulated deviation from the reference point. And there's a third parameter that multiplies the rate of change of the deviation from the reference point. So that's proportional integral derivative. Three parameters, you plug them in there, and merely you go on. Surprisingly successful, and very old, by the way, more than 100 years it's been around. However, in industrial applications, it applies primarily to single input, single output systems. System may be more complicated, but there's only one input and only one output that you multiply with these proportionality constants. And the output is usually the error from some set point. And as I said earlier, the big selling point of this controller is that no mathematical model is needed. And it works in the sense that it doesn't blow up on you in many cases, but doesn't mean that it works optimally, okay? It could be working suboptimally, but that may be fine on some applications. Okay, questions? Okay, so I'm going to into the second type of methodology for adaptive control. It's called indirect adaptive control. Here, essentially, we have an alternation of two phases: a system identification, where we estimate the parameters of the system, and then in the second phase, we re-optimize the controller. So get data from your system, estimate the parameters, feed them in the controller, and the controller changes itself by re-optimizing. For example, if you have a linear quadratic problem underlying here for known parameters were known, the problem would be linear quadratic, the controller recalculates the Riccati equation, and the Riccati controller gain. So if you have a simple re-optimization, then that's perfectly very quick. So that's the idea. Recompute the controller, so it's often for a current set of parameters. Sometimes it's easy, but also it can be very time consuming. There are also some theoretical issues associated with this that people in the 70s and the 80s have dealt extensively. In the 70s and the 80s, there was a lot of work on system identification. There still continues to be a lot of work on system identification, but that was the heyday. And people studied the interaction between the parameter estimation context and the choices of control. They found some strange phenomena where, by simultaneously estimating parameters and controlling the system, the application of control would shield some of the system parameters from identification, and the whole thing may fail. And there's an example like that in your textbook. If you look at the adaptive control section in chapter 1, there's an example like that. A lot of theoretical work went into that. A lot of analysis, and generally speaking, people have found ways to deal with that. But I don't want you to leave with the impression that there's no theory behind all this. There's a lot of theory and a lot of work that took place since the 60s. Okay, so now I'm going to focus on this part here, time consuming. This is time consuming, and I'm going to make it less time consuming by approximating this re-optimization. Oh, before I do that, let me give you this example. Okay, I'm going to compare robust control and online replanning using re-optimization. Remember, our robust controller is kind of naive, doesn't care about estimating parameters and all that. And the previous slide uses a re-optimized policy after you estimate the parameters. And this example is linear quadratic. This is one-dimensional linear quadratic, and B is a parameter that's changing, okay, and is estimated. The cost is infinite dimensional quadratic. R is a given parameter, and okay, so the robust controller is calculated for a nominal value of B equal to 2, okay? As B changes, its performance, as measured by the corresponding coefficient, capital K, the cost coefficient of the controller, this is the performance. The exactly re-optimized policy is better. This corresponds to the fixed controller for B equals 2. This performance is obtained by measuring B exactly and applying the optimal linear quadratic solution. So this is the price you pay, the pricing cost that you pay for using robustness, relying on robustness rather than exact estimation of B. And you can see that, okay, for B equals to 2, the performance of the two coincides, but as you go, particularly if you go, B changes on the left, which means that you need much larger controls, okay, to bring the system towards 0. And these larger controls, the error due to the large control is amplified, okay? You can you can sort of think through what's happening here and see why the performance gets much worse on the left rather than on the right. But you can see that there's a price to be paid. Okay, so I'm going to come back to this figure, but what I'm going to focus now is, instead of reoptimization, use an approximation to that, like rollout in this particular case, or approximation in value space. So we're going to deal now with online replanning by rollout or approximation in value space. And again, we estimate the parameters. We assume that there's some kind of a computational cloud here, an environment that changes the system parameters, the cost, perhaps some constraint parameters. And all of this information comes into the controller, who estimates the values, the unknown values, the B in the case of the previous slide. And what we have is the approximation value space, the architecture that we have been using. At state xk, we minimize over the next possible, we consider all possible next states, and then take a cost function approximation, perhaps with intermediate rollout with a base policy. Now, we argued that if the cost function approximation is reasonably good, and Newton's method applies, and so on and so forth, then this approximate optimization is almost as good as the real optimization, the complete optimization, but also faster. So instead of using reoptimization, we have some kind of robust controller to generate this rollout, and we have some cost approximation, perhaps trained with a neural network or whatever you have, and you, instead of reoptimizing, you do this approximation value space calculation. It's also possible, as you collect information about the parameters, to recalculate the base policy to bring it more in tune to the changing parameters. A lot of games you can play here. This architecture has been tested in some examples. It works very well, but it hasn't been tested enough. It's a new idea, well, a few years now. And those of you who might be interested in control theory applications, it's a good area for a term paper to try out. Any questions? So we have robust control to do adaptive control. We have three approaches: robust control, indirect adaptive control with reoptimization or with rollout approximation value space. And okay, again, let me go through this slide. It's the same example as before, where B is an unknown parameter. And I'm comparing here the robust controller, the exactly reoptimized controller, which is this black curve here. And now I'm superimposing the figure, the performance of the approximately reoptimized rollout policy with one step look ahead. And the performance of these two is indistinguishable, very, very close. Not exactly the same, but very, very close. And what is this difference? Well, it's the power of Newton's method. That's what it is. Newton's method has just gotten you very close to the optimum, and it's not necessary to do this exact reoptimization. So in limited examples, in a limited set of examples, this idea looks very good and very effective. And it's representative of, it falls into the category of indirect adaptive control. And we mentioned three approaches: robust, indirect, and now the third approach is the POMDP approach for adaptive control. Okay, so let's try to interpret this figure here. we have a system that involves an unknown parameter, theta. Here we explicitly consider the unknown parameter, and we assume that this unknown parameter takes values in some set. And for simplicity, I assume here that the set can take m possible, that the theta can take m possible values, which are known. You know the values, but you don't know which one is in effect at any given time. And you look at the state of the system, xk, and that tells you about which theta happens to be active at the present time. And it triggers a belief estimator, and this is the belief of theta. It's a probability distribution of theta given all the observations that you got so far. So you try to estimate theta here and construct this belief state, the probability distribution of each value of theta, given all the information that you have obtained up to this point. And we view also theta as part of an augmented state augmentation, and a perfectly observable part, and a part that's not observed at all, but can be inferred through the observations of xk. And now the POMDP exact dynamic programming algorithm applies. The algorithm I gave into the second or third slide in this lecture. And it takes this form. Optimal cost to go at a given information vector involves the sum of two terms. One is the expected cost. This is the expected cost. The cost values corresponding to the different values of the parameters, but weighted according to the probabilities of these parameters. So this is expected cost because this B is a probability distribution. And the second term is optimal cost to go from the next information state, which is ik, xk plus 1, and uk. And it involves theta over here. So it's a random variable, and it's weighted again with the corresponding probabilities, bki, the components of the belief state. So this is an exact dynamic programming equation for the reformulated problem, or reformulated as a POMDP. If you're a mathematician, it takes some mathematical proof to do that. But actually, the proof is very simple, and it's given somewhat later in your text in chapter 2, I think. But for the moment, let's accept it and realize also that there are a number of difficulties for executing this algorithm here. To begin with, is a curse of dimensionality, a horrific curse of dimensionality, because this ik is very, very large in dimension, and how are you going to calculate all these things? It's very difficult. There's also the additional challenge of this belief estimator, but this is the minor evil relative to the curse of dimensionality. So how do we deal with that? Well, approximation in value space. Instead of these j stars that we don't know, we use some j tildes, but we can tailor j tilde to depend on the parameter itself, because we're taking the expectation. So for example, and then we minimize over UK to obtain one-step look-ahead policy. So if I somehow can calculate this j tildes, then I can do this minimization and obtain a one-step look-ahead policy. Now, what would you choose as j tilde of I? You can take it to be the clairvoyant optimal cost function, clairvoyant in the sense that we know theta I. So assuming that I know theta I, then the corresponding problem may be easy. It may be a linear quadratic problem that can be solved in closed form. And its cost function can be calculated. It depends on theta, okay, the value of theta. And we plug it into this calculation, and we take the expected value according to the prevailing belief state and calculate its expression and minimize it. So that's one possibility. A second possibility is to use some form of rollout or other type of approximation value space, where I use an approximation to the cost function of the optimal policy, in particular cost function of some known policy, again, under the clairvoyant assumption that we know theta I. So we plug in here a good policy for the value theta 1, a good policy for the value theta 2, theta 3, and so on. Calculate all these rollout, these cost functions of the policy corresponding to the different values of theta, average them out with the current beliefs, and then you have a computation that may be tractable. Now, out of all this approach, are there any questions about this approach? Like I said, this is a principal approach. It does not a priori separate the problem into identification and optimization problem. It addresses the real problem where you have unknown parameters with a given initial distribution, and you estimate these parameters online.
Professor, I have a question.
Okay.
So parameter theta is only used to generate the augmented state given the xk, right?
Yes.
So a known policy assuming theta equals theta I is basically, is theta itself a policy, or?
Well, theta is a parameter. Let's say theta 1 is the system is operating fine. Theta 2 being one of the engines has failed. Theta 3 is all engines have failed and we're going down. Okay.
Okay. And theta is like,
it characterizes the dynamic equation, the equation that
okay.
According to which xk is generated.
Okay, got it. Thanks.
Okay, so what I wanted to say is that even though this approach is the most principled one, it's also the most difficult to apply. If you take your run-of-the-mill problem and try to apply this approach to it, it's very difficult to apply it because it involves these belief estimators and calculation may be over here, may be difficult. However, it has found more recently a application in some special types of problems that involve sequential estimation and Bayesian optimization. We're going to talk about Bayesian optimization later as a form of sequential parameter estimation. And I'm going to give you an example of that. The puzzle of Wordle, okay? May seem implausible to you that Wordle is an adaptive control problem. And I suppose that most of you have heard of Wordle, right? Is there anyone haven't heard of Wordle? Okay, I hadn't heard of Wordle when I first got into this research, but so I can fully understand. I still don't know how to play it, but together with two students from ASU, we studied an algorithm for approximately optimizing a strategy to play Wordle. Okay. So how does Wordle fit into the picture? Wordle involves guessing some unknown mystery word by making guesses. The list of mystery words is given ahead of time, but you just don't know which one has been chosen. In a practical setting, there's every day in the New York Times a Wordle puzzle that's being published, and the editor chooses a mystery word from a given list that has 2,500 words, and the reader tries to guess this mystery word by making successive guesses. In the New York Times versions, there are two versions. In the New York Times version, the guesses have 5 letters, and the mystery word also has 5 letters. And like I said, there are 2,500 mystery words, possible mystery words. And there are like 12,500 guess words that you can choose from. Now, with each word that you choose, you get some feedback about the commonality of letters within from the guess word to the mystery word. And this feedback is used to select the new guesses. So it's a problem of sequential estimation. You make a guess, and then according to the results of this guess, you do some estimation and get a new guess and so on. So previous outcomes affect and guide future choices. And that sort of thing happens in a lot of other contexts of sequential estimation. In fact, the word puzzle is not a new game. It's a special case of a broader class of puzzles that has been around for decades. Class of puzzles called Mastermind. Mastermind is a game that was invented at the time of Monopoly. Okay, it's sort of a board game of some form, and Wordle is a special case of that class of problems. So, and also there are problems that are outside the world of games, like sequential decoding, okay? Trying to break a code and making some guesses, get information, somehow estimate how successful you were, and this guides the future guesses. Essentially, here you are decoding. You are decoding the puzzle to find the mystery word with successive guesses. So how do we put this into the framework of adaptive control that we have discussed? Well, theta is the mystery word. So it takes 2,500 values from a list. According to a given probability distribution, initially, and it is in the New York Times version, this probability distribution is uniform. All mystery words have equal probability. This simplifies the problem a great deal. However, okay, we view theta as part of the augmented state, with xk, the state being the list of possible mystery words. So initially, the list of possible mystery words is 2,500 long. After you get the first guess, then that list shrinks because some words are eliminated, are incompatible with a guess. It shrinks and shrinks and shrinks. So that's the state. And a nice thing about this puzzle is that this list continues to have a uniform probability distribution. So you don't have to maintain a probability distribution over the set of eligible mystery words. All you have to have is the list itself. So that helps a lot in the computations. And if you didn't have this property, or uniform probability distribution, the problem would have become much more difficult. So this xk is the list of possible mystery, and it's perfectly observed. UK we control is the guess word that we choose, and theta is the unknown mystery word. And just to make things more clear here, particularly since we have people in the audience who are not familiar with this game, suppose that the mystery word chosen is this one here, inert, okay? And you make a first guess, audio. Then you get a response from this. And the response has to do with the commonality of letters between your guess and the mystery word. In this particular case, there's one common letter, which is I, but it is not in the correct position. So you get a yellow response for I, okay? Then you choose a new guess word. Let's say you choose the word stern. Doesn't have to be a mystery word. It's one out of the list of eligible guess words. And then what is the response that you get? You get the response that there are 4 common letters between this word here and the mystery word. E and R are in the correct positions. So you get a green light, a green response for the 3rd and 4th position. And T and N are in the wrong positions. So you get feedback that these 2 words belong to the mystery word, but they are not in the right positions. So after the second guess, you have all the letters. You have 4 from here and another one from here. And you have to guess a word knowing that it's an anagram of some form, a meaningful anagram of these 5 letters. And then, okay, experienced players can guess that this is inert. You have all the letters. Okay. So the cost for this, your cost for this puzzle was 2. You required 2 guesses to come to a successful answer. And we formulate the problem as finding a strategy that on the average gives you the correct answer with a minimum number of guesses. Now, if you have 5 chances. So if you don't guess the mystery word in 5 tries, then your score is 5, and that's the end of the game. Okay, you failed to solve the puzzle. So we have all the elements of dynamic programming in partial adaptive system, partial state observation. There's a system, the one that guides the evolution of XK. There's an unknown mystery word. We estimate that. We form the belief state of that. The belief state is a uniform probability distribution over the list of mystery words. We choose a guessed word, and it's possible to use some heuristic for that. And there are quite a few heuristics actually in the literature for playing Wordle. Some of the most successful ones are based on information theory concepts. Okay, so you have all this feedback that you have gotten from previous guesses, and then you calculate which one of the remaining guesses is the most informative. It has the maximum information gain as calculated by entropy concepts of information theory. Gives the most reduction in entropy of the mystery list. Entropy has to do with uncertainty. Okay, if you're not familiar with information theory, I won't be able to explain this to you, but it's a very intuitive concept here. Each guess gives us information, and we find the guess that has maximum information gain. Okay, that's the base of the heuristic. It's the most successful heuristic. There are also other heuristics. For example, one considers all possible guess words and tries to minimize the length of the mystery list. So you have 2,500 words, then it shrinks down to 1,000, and then you look at various guesses, and then for different guesses you can figure out the size of the next mystery list. So one guess word gives you a list of 100, another one 110, another one of 95, and you choose the guess that minimizes the length of the mystery list. Okay, that's another heuristic that's also fairly successful, and there are quite a few others that I'm not going to get into. Given any one of those heuristics, you can roll it out and look into the future on how it's going to do by using these heuristic actions. And that improves on the performance of the heuristic. Remember, rollout, if you want to, one way to describe it is a method for improving the performance of any suboptimal policy, including the performance of any heuristic. So there was a term paper in the 2022 offering of this class by 2 of graduate students, Siddhant Bambri and Amrita Bhattacharjee, and they implemented rollout with several different heuristics on Wordle, the standard version of Wordle, and they were very successful with that. And then we did subsequent computations. So we have an archive paper online. There's also a conference paper that has been published. And I'm going to have Siddhant and Amrita come here in a later lecture, probably in 6 lectures or so, and they're going to describe their work. But the result is the following. It is possible to calculate the optimal strategy for Wordle, for the New York Times version of Wordle. it takes many days. It's a gigantic dynamic programming computation, taking advantage of all the structure of the problem, the fact that the initial probability distribution is uniform, cutting corners here and there, being clever, using parallel computation. Still, it takes quite a few days to do this computation, to find the optimal strategy. And it's calculated that with optimal choice of the initial word, the optimal value, the optimal average number of guesses is 3.5, about 3.5084. Now, our rollout algorithm gives you an answer online within seconds. Okay, it's just very fast because, okay, the heuristic is fast. And the performance with that is less than half of 1%. For all practical purposes, it's an optimal performance. And also, it scales with problem size. So if you had a puzzle with 6 letters, 7 letters, then it would be infeasible to calculate the optimal strategy for that. However, the rollout has no problem. It just takes a little bit more, but it's in the order of seconds again. So anyway, this was a fun project and has been successful, and also the starting point for other investigations involving sequential estimation and Bayesian optimization, because this has the character of sequential estimation. But that will take us, that's for a different lecture, not today. So time to take a break. Are there any questions here? Okay, so we'll see you in 15 minutes. Okay, guys, it's time to get started. Have any questions?
Professor, I have a question. So
Yes.
can you go to slide 12? So in this picture, so if taken the adaptive cruise control on the self-driving car example, can you say that when using robust controller, we're actually, for example, if the controller wants to keep the car in a straight line, right? When using robust controller, it's kind of car is swerving around the central lines. Is that like imagination practical? For example, because it doesn't have access to the optimized policy, so it's like when it's slightly on the right hand side, it turns left over the central line and then turns it back. So it's kind of driving an S line. Can I understand it that way?
Okay, so this slide is a mathematical example. Does
Yeah.
not have to do with the cruise control example, which involved, as you remember, involved trying to regulate the speed of the vehicle around some set point, this X bar.
Sure.
Now, that speed is only in one direction. That car is not swerving. It goes on straight line. That's the model. It's in a lane and regulating the speed of the car going along the highway lane.
Okay.
So, okay, so.
So
I
in
hope
this example, it's just like driving slightly faster than it, and then just put on the pedal and stop the car and then accelerate again. Similar to that, right?
Yeah.
Okay.
Yeah, but it does it automatically. The cruise control, okay. I mean, I have a car that has cruise control, and what it does is you set it at a certain speed, and it regulates the speed of the car according to this setting. Now, the car may slow down because it's going, for example, all of a sudden goes on an uphill, or it may accelerate because it's on a downhill. The cruise control will keep it at a steady speed.
Got it.
Okay. Okay, so now we'll go into model predictive control. It is one of the most popular, perhaps the dominant methodology for sophisticated control problems. And let me remind you that what control theory is about. It involves systems that have multidimensional states, which are vectors, n-dimensional vectors. Like in three-dimensional space, there might be a six-dimensional vector specifying the position of a vehicle or a moving object. Three-state variables for position, three-state variables for velocity. And there are two basic problems. One is control around a reference point, and the other is control along a trajectory. These are the classical problems of control theory. And I think I've talked about that in one of the first lectures. This is a picture of a regulation problem where we want to keep the state of a system close to zero in this particular case. Theta is a single is the angle of a rod with a mass at the end, the angle from the vertical, and theta bar is the rate of change. Theta dot is the derivative of theta. This theta is a function of time, so this is theta dot is a derivative of the derivative of this angle. Okay, in this example, the system is continuous time, but imagine it as being discretized. Conceptually, however, the problem is how to keep this rod vertical and relatively at rest without moving very much by using horizontal force on this cart. This is mostly an academic example. You may have tried also by yourself with a stick to balance it on your finger. It's a non-trivial control theory example. That's why it's popular in control theory courses. The second example, the second type of problem is path planning, whereby you want to take a system from some initial state, some final state, along some trajectory, which is given to you. And there may be constraints, all kinds of constraints, velocity constraints, acceleration constraints, obstacles like walls or buildings, and also moving obstacles like other cars. And state constraints here are very important. You don't want to crash your car on a wall or on another vehicle. And because some of these constraints are unpredictable, you may have to do online path replanning. These are difficult problems. Alpha zero is a trivial problem relative to sophisticated versions of this problem here. Extremely difficult. And it's amazing to me that there are self-driving cars around. I just marvel at them, and I'm blown off. So control theory is current and also challenging. And model predictive control is one of the primary methodologies and a sophisticated methodology for dealing with such problems. Methodology goes back to the 80s, late 80s. And I'm going to give you here the original form of the model predictive control formulation. I'm going to be using the term MPC, model predictive control. So in the original form of MPC, you have this system that is deterministic. There's a cost that's positive, except at the origin where the cost is zero. And it's positive everywhere else. So the objective, roughly speaking, here is to control the system so that it stays near the origin. And the way it works is as follows. We are at a given state, xk, and we minimize the cost function, the sum of these costs, over the next L stages, while requiring that L stages ahead, the state is going to be 0. So we would like to keep the state near 0. We formulate MPC as aiming to reach 0 in L steps while minimizing the cost. That gives us a sequence of controls that accomplishes this transfer. And we apply the first control of the minimizing sequence and discard all the others. So it has the character of approximation in value space. Remember, in approximation value space, we do multi-step look ahead, perhaps followed by cost function approximation, rollout, and so on. And then we get a sequence from that look ahead minimization problem. We use only the first term of the sequence and throw away all the rest. And indeed, if you look at this formulation, it is rollout. It's the same thing as rollout. And what is the base heuristic here? Well, this is a one-step look ahead. And here, the values that we pick up from here are the costs of the policy that takes us from any one of these states to 0 and stays there thereafter. So that's my base heuristic. Instead of optimally planning my trajectory through the infinite horizon, I just plan my trajectory to get me to 0 and to stay there. That's a suboptimal control sequence. But that's what I use as rollout. So one step look ahead and roll out after that. With another view, you may consider this requirement that the state be 0 after L steps as a form of cost function approximation at the end. So you can view this as an L step look ahead with cost function approximation that is 0 at 0 and it's infinity outside 0, okay? Infinite penalty for not being at 0. Whichever way you view it, it is very much like approximation in value space. It inherits some of the good properties of approximation in value space in the sense that it's well suited for online replanning. So if the system equation changes or the cost changes or some constraints change, then you still do the same thing, except that you incorporate the new problem data into this minimization. Now, the original formulation, and for the moment, we're going to neglect state constraints, which turn out to be very important in the context of MPC. But we'll just disregard them for the moment and deal with them later. This is the original form, but people quickly came up with extensions and involving the look-ahead minimization. In this particular variation of MPC, instead of driving the state to 0 in L steps from the current state, we use a terminal cost function approximation, G. So the problem that we solve is minimize over the L steps, the terminal cost plus the cost of the L stages, and get a sequence out of which you keep the first one and apply it and throw away the rest. So without this middle box here, it is approximation in value space with multi-step look ahead, L step look ahead. You can also introduce truncated rollout with some policy, some stable policy. It's important that the policy be stable. And this gives you a more general architecture, which is exactly the same as the alpha 0 and TD Gammon architecture. The circumstances in which these are applied to control theory problems, and whereas alpha 0 and TD Gammon is applied to games, but the architecture is the same. And the ideas of approximation in value space and rollout are also the same. Now, in MPC applications, there may be also state constraints, and that complicates the matter, and we'll deal with those in a few slides. But a principal question here is, when is the MPC policy stable? Remember, we discussed stability in the context of multi-step of approximation in value space. So an important question with which people have dealt with extensively, because stability is very important in control theory, is when is the MPC policy, the policy that you obtain at the L step look ahead policy, when is it stable? And the answer to this can be understood by looking at the diagrams that you had for your homework. G must lie in the region of stability. The region of stability for L step look ahead, which is the real region of stability with one step look ahead, but enlarged thanks to L step look ahead, and also possibly enlarged because of rollout. So that's where the value of multi-step look ahead and the truncated rollout come in the context of MPC. They tend to provide policies that are stable, and that's important. The choice of G is also very important, and people have looked into that. And by the way, Yu Chao, our co-instructor, did his PhD thesis here on precisely this question, on finding conditions on how you design the terminal cost approximation based on the ideas of Newton's method and the ideas that we did in the previous lecture. How do we incorporate them into practical designs? So you have questions in this area, we have the perfect person here to ask them. Okay. Any questions here? For me or Yu Chao? So let's go to the issue of state constraints. I gave you earlier the example of the car trying to go on a given trajectory. It's obvious that state constraints can be very important in a number of control settings. So how do we modify the problem? Suppose that we have constraints of this form. Xk must be in some set of the subset of the state space. Then the MPC problem that has to be solved at the K stage must be modified to incorporate the state constraints. So assuming that the current state satisfies the state constraint, the MPC problem minimizes the sum of the terminal cost and the cost over the L steps of the look ahead, subject to the control constraints and the additional state constraints. So part of the problem here is, given a state in here, keep the state in this set capital X. So there is this requirement. We have to be able to generate a state within capital X and the next state, given any state in X. So you want to keep the state of the system within this set. But this is not so easy. It's actually a subtle question, because there is no guarantee that this problem has a feasible solution. In other words, there's no guarantee that there are no bad states within X from which we cannot keep the state of the system within X. So this state constraint has to be carefully designed so that we can satisfy it through MPC. This leads to the concept of invariant sets, which is important in MPC. And let me explain them in terms of an example. Let's consider state constraints for a one-dimensional problem that are an interval. Here, the requirement is to keep the state of the system within beta distance from 0. And the system that I have chosen for this example is unstable. It has this form. So from state xk, the state tends to increase gets doubled and has to be brought back towards 0 with proper choice of UK. On the other hand, if the control is also constrained, so if beta is greater than 1, you start at states larger than 1 or less minus 1, then you can't bring the state back to system towards zero. The reason is that if you take x0 to be beta greater than 1, then 2x0 is going to be greater than 2. And the next state, no matter how large you pick the control in the opposite direction, the next state is going to be larger than x0. So if you start within this red region, no matter how hard you try, the state of the system is going to keep increasing because you have limited control. You cannot bring it back towards 0. So for this kind of state constraints, MPC is not, no matter how hard you try, MPC is going to be unstable. You need to design the set constraint, the state constraint, so that you can have a feasible control policy that leads you towards 0, to obtain stability, in other words. Now, what would be a suitable state constraint? Well, there are these invariant sets. In this particular case, the set between 1 and -1, where if you start inside this interval, then even though the state is going to increase due to this term, the control is sufficiently large to counteract this increase and bring you towards 0. Is this clear? You can take values between 1 and -1. If x is large, then 2x is going to be twice as large, and no matter what u is, x is going to be increasing. So you have to choose your initial u within some region, and this region is between 1 and -1 to be able, with proper choice of control, to bring the state towards 0. Now, sets like this are called invariant, in the sense that if you start within such an invariant set, it is possible to choose control to keep the state within the invariant set. In other words, it's a region within which the system can be confined with proper state of control. They are invariant in the sense that you can get out of them. So this is the definition. To guarantee feasibility of the MPC problem with state constraints, capital X must satisfy an invariant condition. For every X within this constraint set, there must exist a U such that the next state can stay within X. Then you're guaranteed that there is a policy that will keep the state feasible within the region. So, okay, if you have a constraint like keeping the car within the road because there are obstacles right and left, okay? And suppose that there is a turn here, and you have a constraint on how fast you can take the turn. If you take the turn too fast, like you'll get off the road, right? And however, if you're already going at a high speed, then even if you push the brakes as hard as possible, you may still get out of the road because your control is not high enough to brake the system in time. So as you go on the turn, your speed has to be within certain limits. Otherwise, the car is going to get off the road. That's the invariant set. The speed has to be within a region where you can satisfy the constraints for the future. Okay. I hope this explains it somewhat better. Okay, so there are only some state constraints that qualify for use in MPC. But how do you compute such sets? To compute an invariant set is a difficult problem. How do you find them? And necessarily, this is an offline calculation. You can't do it. You can't do it online. It's just too difficult a calculation to do. It has to be done offline, and there is theory about these invariant sets. It turns out for any given constraint set, there's a largest possible invariant subset of X, and it can be computed in the limit by algorithms that sort of resemble value iteration. Now, suppose you have calculated an invariant subset of the state constraint, you use an NPC, you make sure that you start within the set, and you know that the MPC controller is able to keep that system within that set. You don't necessarily have to calculate the largest possible invariant subset. It's enough to calculate a subset, which is invariant, and this is a possibility, and which is actually a more practical possibility. I see you have a question from online. Go ahead.
Yes. So for invariant sets, so if the problem, if a problem is deterministic, I think it's easy to understand. But the problem is, if the problem is stochastic, then how can you? Because some noise can happen to the state, and typically, like if you model with Gaussian noise, then always maybe with some non-zero probability, your system may go out of the invariant set due to the presence of the either unmodeled disturbance of the noise. So does it make it really hard to do for the stochastic system, or do they just assume invariant set given the noise is zero or the uncertainty is zero?
No, you have to take into account the noise because you don't want to crash on an obstacle. Under worst case, you have to take into account not the noise and the uncertainty in the system or in the system equation. You have to take into account with our worst case point of view. In other words, the description should not be probabilistic. You should be able to keep the state of the system within the invariant set for all possible values of the uncertainty. So it's a minimax viewpoint that has to be used for this, and a set description of the uncertainty. In other words, that the W that you have
has to be bounded. You cannot use Gaussian noise.
Bounded, yes.
Yes.
Then it's
yeah.
Bounded.
And that's a restriction, right? Because like Gaussian noise is like common, so it means you cannot use it in your modeling if you're gonna use this kind of modeling, because the Gaussian can go from -infinity to infinity.
No, you cannot use a Gaussian uncertainty. You have to use a bounded uncertainty and modify the invariant set to account for the worst possible value of the uncertainty.
So maybe if you have a Gaussian, maybe you take the 95% confidence interval or 99% confidence interval, and then it will be bounded. Like, is it flexible like that?
Yeah, then you have a probability of 95% not to crash.
Or 99%, which is maybe good. But okay, I understand.
Yeah, okay. Actually, okay, let me tell you the story of this. There is the original formulation of invariant sets involved uncertainty, and it's very old. It goes back more than 50 years. And I know the exact date and time when this idea was generated. And the reason is that I was the one who introduced invariant sets and the idea of invariant sets even in the presence of uncertainty. The uncertainty at that time was called unknown but bounded uncertainty. And there was work on estimation of systems with unknown but bounded uncertainty and so on. I was driving from my home to MIT on trying to follow the road and not to crash on any other cars. And this idea came to me and was actually a major part of my PhD thesis, which dealt with set members by uncertainty, for estimation, and for control. The control part had to do with the use of invariant sets of or target tubes, as they were called then, and they're still called target tubes in the concept in the context of MPC. So anyway, nobody paid any attention to my thesis for a long time, like 15, 20 years. And then eventually the idea of invariant sets became understood that that it was a useful idea in the context of MPC and also in other contexts. And a few other people also came along this idea after me, like several years after me, and they published papers, and my thesis was not noticed very much. That was quite upsetting to me. So, but eventually, okay, I got credit eventually, and my thesis was the first. So here's an assignment for you guys. If you go into a cocktail party and somebody tells you that he's the one who invented invariant sets, I want you to say no. It was Professor Bertsikas that invented invariant sets in his PhD thesis, and then write to me, and I'll be very happy that you did that. Okay. So with this now, we have concluded the introductory 4-lecture portion of our course. And I have a couple of slides more that are overview. What we have tried to do is to set a foundation for a deeper development of reinforcement learning topics in future lectures, and also importantly, get to a stage where you can get started with your term paper. And next week, I'm going to give guidelines about the term paper. But basically, you can go in any direction you want for your term paper, but I think the first 4 lectures give you the broad picture of the reinforcement learning landscape within which you can start exploring. So we have described the following: the algorithmic foundation of exact dynamic programming in all its major forms: deterministic and stochastic, discrete and continuous, finite and infinite horizon. The foundation is dynamic programming. This is not going to change. The field may evolve, but dynamic programming will continue to be the foundation. That's part and parcel of reinforcement learning. We have spent a lot of time on approximation in value space with one-step and multi-step look ahead. This is the workhorse of reinforcement learning and underlies its major success stories like AlphaZero, TD Gammon, and so, and MPC. There's a fundamental division between offline training and online play. There are 2 algorithms involved here, and they don't need to be related to each other. On the other hand, they are synergistic, and their synergy is encoded into this Newton step interpretation. And online play built on top of offline training improves performance a lot. That's an important fact to keep in mind within the context of reinforcement learning. Fundamental methods are policy iteration, self-learning, the Alderney, TD Gammon, AlphaZero, and also rollout, which is also important within similar context. However, policy iteration is primarily an offline method because you have to learn cost functions and policies repeatedly, and that requires the use of neural networks, training with neural networks, and that takes a lot of time and cannot be done online. It has to be done offline. Rollout, on the other hand, is an online method. It's a one-shot policy iteration. It's an online method, and it works well because it connects with Newton's method. It's one step of Newton's method, and it tends to work very well in theory and in practice. But it's less ambitious. If you want to go ambitious, you should try to do repeated rollout. First, get a cost improvement and policy improvement with rollout, then get a policy improvement on the policy improvement, and so on. Okay, we cover some major models within the broad range of applications, discrete optimization, POMDP, multi-agent problems, adaptive and model predictive control. And in all these, function approximation is central and has been a recurring theme. And we have talked about function approximation, but we didn't discuss how you do function approximation. And that we will do later when we talk about neural networks, feature-based architectures, and also the newer architectures based on pre-trained transformers, the GPTs. The GPTs are going to be a game changer. They're more powerful than the traditional neural networks. They're more flexible. And they are also pre-trained. You can get somebody else's GPT and use it on your application. You don't have to train your own. Or you can get somebody else's GPT, like from OpenAI or Facebook, and then do extra training on it. And then it becomes more powerful and better suited for your application. Now, this is a broad new area that's opening up. We're exploring it, and I hope we have a chance to do that in future lectures in this course. So let's look at what lies ahead. Your textbook has 3 chapters. Chapter 1 is foundational, the stuff that we have covered so far. Chapter 2 deals with rollout, its variants, and its applications in various contexts, including multi-agent, stochastic, and so on. Chapter 2 also deals with sequential decision-making in special context, like sequential estimation, Bayesian optimization, and various aspects of simultaneous identification and control that arise in adaptive control. Chapter 3, which is going to be probably 3 lectures in this, at least 3 lectures in this class near the end or at the end, is going to deal with offline training for approximation in value space and approximation in policy space, using neural networks, perhaps even GPTs, even if we can understand them by that time. Otherwise, it's going to be for a future offering of the course. Well, neural networks and their training is discussed in chapter 3, at least the principles of the training of neural networks. Now, there are a lot of other topics in reinforcement learning that we're not going to cover. There are stochastic algorithms such as temporal difference methods and Q-learning. These have been important for the development of the field. You'll see a lot of literature about them. They are used for offline policy evaluation and also for approximate policy iteration. But not only they are mathematically challenging to understand, but also their influence has been going down. And I project that they're not going to be the dominant methods of the future. Very few people talk about temporal difference methods at present. There's more talk about Q-learning, but I think this methodology has some serious limitations. And given what's coming ahead, the methodology is going to go down in significance. Statistical type of problems having to do with sampling methods for collecting data for offline training. They are important, and but it's a subject that we're not going to go into, primarily because, again, this type of methodology is going to be, I project, de-emphasized in the future. Similarly, a lot of work of a statistical character of error bounds associated with various sampling techniques and simulation techniques. Then the same category, it's a statistical view of reinforcement learning that is not going to be, is going to receive a lot of emphasis in this course. Finally, we're going to be touching upon methodologies like model predictive control, and it has very wide range of applications, a very large literature dating to many, many years, and we cannot hope to provide a deep exploration of these methodologies. All of this, there's a lot of literature available, and if your research interests are in this area, you'll have to read beyond this course to get deeply into them. So that's what we have done, and that's what we will cover and we will not cover. And starting in the next lecture, we're going to go more deeply into rollout problems, both for deterministic settings and also for stochastic settings. There's not going to be any homework for next week, but we're going to have a last homework in the week. We're going to announce it next week. There's a video lecture which will cover pretty much the next lecture, and you may consult it if you want to come better prepared to better prepare next Wednesday. Also, like I said, next week we're going to pass around some guidelines for term papers so that you can start thinking about your work on the basis of these guidelines. Okay. Any questions? Okay, guys, see you next week.